Okay. So I'm from EPFL. EPFL is École Polytechnique Fédérale de Lausanne. So I'm going to spend a couple of minutes to tell you where this is. This is Lausanne, which is close to a lake. And lake is called Lac Léman. This is Switzerland over there. And this lake is the biggest lake in Europe, in Western Europe. And it's not the biggest lake in Switzerland. Why? No, it's the biggest. Yes, because this is France. So Lausanne is just in front of France. So this is France. This is Mont Blanc, if you heard about the famous mountain. So Lausanne is nicely located. So it has École Polytechnique Fédérale de Lausanne. There are two of these schools. One of them in Zurich, called École Polytechnique of Zurich, ETH Zurich. And there is Lausanne. It's actually the same institute, although we keep fighting all the time, but it's the same institute. Zurich and Lausanne. In Lausanne, there are about 8,000 students, and I don't know how many departments. The computer science and communication department has about 45 professors, and each professor has a lab from between 20 to 30 people in different areas, and we are typically looking for always for visitors, sabbatics, students, etc. So it's a good place to go. I have had very good Russian students from Moscow and St. Petersburg, and I was very happy with them. So this is Lausanne, and this is about 1 hour from EPFL in the winter, so we have nice skiing places, so you don't only work. And in the summer, this is about 100 meters from EPFL. So both in the summer and the winter, there are things to do besides working. Okay. I'm going to talk to you about something I call adversary-oriented computing. So this is actually a new, at least a new name for an idea that is to some extent new. Okay, so in short, and please stop me if what I'm going to say is not clear to you. This idea that I'm going to talk about is a way to simplify the problem of writing concurrent and distributed programs. Who has ever written a concurrent or distributed program? Okay, good. So you all know that it's very hard. It's much, 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 much harder than writing sequential programs. It's hard to test, hard to prove, it's hard to debug, it's hard to maintain. It's very difficult. And this adversary-oriented computing is a promise, it's just a promise, to simplify this problem. So the name came from the following. The European Commission has a research council, and every year it opens some competition for people to apply and say, I want to solve this big problem. And if they select your project, you get a lot of money. Not for you, unfortunately, but you get a lot of money to run the project. And you need a good name, because you have this experts committee who are there sitting, they look at your applications, you need a name. So the name came from there, so I applied, and I got actually 2.5 million euros to work on this, unfortunately not for me, but to sponsor students and visitors. So this is a new project and the new name, which has to be sexy in order to attract attention. Okay, but there is something behind the sexy name. At least I like to think that there is something behind the sexy name. And this is what I'm going to explain. But what I'm going to explain is more precisely the following. What is actually the big problem, or at least a big problem, in writing concurrent and distributed algorithms? And once we know what the problem is, then this comes almost trivially. So the talk will be divided into 3 parts. First is some observation about what happens when we move from centralized to distributed. It's important here to notice that what I call distributed is, generally speaking, anything that has multiple processors. So this is a distributed machine. I guess it has at least 2. So the term distributed is general. And then the second part of the talk, I will highlight some observations where we actually move from algorithms to systems, where we really want something to be running. And there is something that is actually difficult. And then I will talk about adversary-oriented computing. Okay. So assume you want to write an e-commerce application. So you get hired by Yandex, and they tell you, we want to compete with Amazon, and We want to be able to write some, maybe there's already an Amazon Prime here, I don't know. But assume this is the game. So they ask you, we want to compete with Amazon. Let's start thinking about the design of an simple Amazon system. So it's a web commerce application. You get some requests from customers or clients all over the world, and you have to treat those requests, store them somewhere, get access to some bank, etc. So the first thing you do if you studied computer science is you say, okay, I need to first identify the objects that are going to be the component of my application, right? I'm simplifying things very, very much, but still. So there are at least two objects that will be very important. One of them is a queue. So when I get some requests from my customers, I need to store them in a queue. So there are producers that put those requests in the queue, and then some consumers are going to consume those requests. All e-commerce applications have some queue, typically a FIFO, first in, first out queue. And then there is somewhere some storage object where I need to remember that I promised this book to this one or these shoes to this one, etc. So at least we have these two objects. I'm simplifying Amazon, but the idea is there. But let's look even more carefully. So we identified the objects that we need. And now we say, okay, let's try to think about how we are going to implement, for example, the queue. Is it clear what a queue is? Everybody is familiar with the queue? Okay. So we want to implement the queue, and we want to implement the storage. So what they have been teaching us, and what I guess your professors have been teaching you, is that, well, in object-oriented or abstract data types, it's very good discipline. You have to first think of the operations that you would like to have on your object. So for the queue, you need to enqueue the queue. Maybe you would need to do other things, but at least you need these two. And for the storage, you need to read and write, at least these operations. Okay, so this is called the design of your system. So far, so good? Okay, good. Next step is, okay, now we need to open these enqueue and dequeue operations and implement them. But before implementing them, let's think of the algorithm. We need to have an algorithm for the enqueue and an algorithm for the dequeue. Okay? The way typically we devise algorithm is we say, well, we need an algorithm that is fast. What do we mean by fast? Usually when we say fast, we have some complexity idea in our mind. We think we want to minimize something. Typically what we want to minimize, at least in the old days, is the number of elementary operations that we have underlying the enqueue and dequeue. And that's the way it is because there was some, what is this? It's written here, but I don't know, maybe you cannot read it. Yeah, because there was this smart guy, Turing machine, who said, well, all computers are equivalent to this simple one. Therefore, we can think about the complexity of a queue by simply thinking of a very simple machine and minimizing the number of steps. Okay, this is how complexity has been so powerful, because there is a universal computer on which we can reason when deciding that this is a good algorithm. So far, so good? Yes, okay. So we have a function complexity that takes as an input the object that you want to implement. For example, if it's the queue, then we will have the complexity of the queue or the complexity of the enqueue and the complexity of the queue. Okay? And this is very nice and beautiful because this function here does not depend on specific computers. The function doesn't change if I go to my Macintosh or I go to an HP computer or whatever. Why? Because there was this smart guy, Turing, who said they're all equivalent. Okay, so this function is very abstract, and this is very powerful. So far, so good? Okay, if I lose you here, it's going to be harder later. So you are with me now? Okay, good. Okay, now let's go back to the e-commerce application really. And we say we want to implement the queue. And we want an algorithm, and we want the algorithm to be fast. Alan Turing told us, don't care about the computer. Just think about an abstract representation of a computer and try to minimize the number of operations to enqueue and the number of operations to the queue, right? Well, this is indeed true because Alan Turing and all people who have been teaching us algorithms have been thinking about one algorithm, one computer, okay? This is the assumption. We are going to run our algorithm on one computer. But does Amazon run queues on one computer? Of course not. And if you want one day to compete with Amazon, you won't implement the queues that are getting the requests from clients on a single computer. Every queue that is receiving requests will be implemented on at least 2 or 3 computers, at least. Why is that? Well, for obvious fault tolerance and scalability reasons. So you won't have a single actual queue, but several. All of them are representing the same one. But the reason why you replicate the state of the queue is because you want to guarantee that if this one on machine A fails, you still have these 2 who are responding. And sometimes it has not even to do with failures, it's just you want to be able to fastly respond to customers. But from a logical perspective, we are still talking about the same queue. It's still the same queue representation from the clients or customers. So now, So now the delicate question is, we want to implement the queue on several machines, therefore we will have several copies of the same queue, and these copies of the same queue are going to communicate. So on an IP network or whatever, because we want to give the impression that we are talking about the same physical queue. Okay? So the game changes a little bit. We don't have an algorithm to be run on a single Turing machine, but we have an algorithm to be run on several Turing machines. Okay? We have a distributed algorithm. And the question now is, what is the complexity of the distributed algorithm? So far, I told you that the complexity of an object or queue is simply parameter of the object of the queue. Now, if I ask you a question, you have to implement a queue, and the queue is on 3 machines. Okay? You replicate the queue on 3 machines, but still the clients should view these as the same one. What is the complexity now? How do you even reason about the complexity? So you can start by saying, okay, now what is important is not the number of individual steps on each Turing machine, but maybe the number of messages, because now messages take a lot more than individual operations, except if you do crypto, but let's say you are not doing crypto. If you are exchanging messages, this becomes important. Okay, let's say this is important. How do you decide that this algorithm is better than that algorithm? What is important here? Synchronization is important, right? But there is something here about the network that is important. This A here, in your opinion, what is it? I'm claiming that there is another parameter that becomes important. Okay, this is the game. I call this the adversary. So when you write an algorithm on an IP network and you want to implement a queue on 3 machines, the question of what is the best algorithm or what is the complexity depends on something very important. The thing that is important is the assumption I am making on the network. Is the network synchronous? Are the channels reliable? Is the load balancer this or that? Is the synchronization that way or this way? All these assumptions are very important. Once I know them, I can say, okay, now I can do my algorithm. We call those assumptions an adversary. Why? Because the entity that is cutting the channels or failing the machines or reordering the processes, you can see it as an adversary fighting your algorithm. Are we together? So if my network is completely clean, synchronous, it's in a nice room, all machines are new, I have fiber optic, whatever, that's like a nice adversary. Because maybe some messages will be slower than others, but usually everything is nice. But if I'm running on top of the internet and messages are crossing thousands of kilometers, etc., and they can be lost, then the adversary is less nicer. So what is important is the adversary. So my claim, the first observation here is, when I go from a centralized to a distributed algorithm, what becomes important is the addition of a new parameter. And this parameter, we call it the adversary. So if you have been studying distributed algorithms, you're probably familiar with the term. If you have been building distributed systems, we simply call it an assumption on the network or an assumption on the multi-core system. So if we go a little bit more abstract, we have a centralized system. A centralized system means what? It means we have one Turing machine, one computer. And this computer I call P1. And what happens is that P1 keeps executing steps. First step, second step, third step. These are the steps of your algorithm. Now, if I go now to a distributed system, where I have two machines, P1 and P2, but my distributed system is very disciplined. It's very nice, very clean. It's sequential. What does it mean to be sequential? It means first P1 executes, for example, 3 steps, and then P2 execute 3 steps, or 4 steps, and then P3 executes, etc. Everything is lockstep. This is a nice distributed system. This is a distributed system because I have already 2 machines, but they're working nicely. Sometimes we talk about synchronous in the following sense. P1 executes, then P2, then P3, and then P1, P2, P3, and then P1, P2, P3. Sometimes we find this in some certain operating systems. So there are, my claim is that there are tons of these. Depending on your environment, you can have this situation, you can have this situation, you can have this situation, etc. This depends on the network, on the operating system, on various parameters. But this is crucial because in the centralized case, there is only one possibility. In the other cases, there can be more possibilities. Each of them is called an adversary. So what is an adversary? Is a set of traces. We call this a trace or a history. If something is not clear, you can stop me. So an adversary is a set of histories. These histories are what? The possible interleaving of my machines. Okay, this is how we can view them. It's just an abstract view. In reality, well, we have processes which are running at a certain speed, but we can view them. We can view their behavior as traces or histories. So an adversary is a set of, we call them runs, histories, executions, whatever, but it's a set. This is the part that is important, is a set. If I have a single machine, the set is a singleton. There is only one possibility. As soon as I have a distributed system, I have more. So what is here important is the following. Some adversaries are, how would I would say, nicer than others. An adversary is nice if the set is small. Why? Because it's easier for me when I design my algorithm if I know that the only possibility is A or B. That's what can happen. But if the adversary is bad, means a lot of things can happen. Okay? So an adversary is a set, and I can have all kinds of adversaries. I can think of the worst adversary is the one where it can attack my network. I have 5 machines, 2 of them can become crazy, or can just start attacking my algorithm. Okay, we talk about malicious processors. So when you do security, you assume these adversaries. When you are a local network like this computer, there is no security problem or whatever, at least I don't care, I'm assuming a small adversary. So the game is, I need to do an algorithm, yes, but now I need to assume an adversary. Okay? Okay, this is the game. These are my processors. I need to write an algorithm on them. For example, remember the queue. I need to write an algorithm that runs on 3 queues, on 3 machines, and models a queue. On the other hand, I need to assume I have an adversary. Okay, and the game is between these guys and this guy. This is the novelty of moving from centralized to distributed. Of course, if you have all done this, maybe you don't call these things adversary, but you have been doing this. If you have multi-threading, right, you have an adversary that is of a certain size because you have a set of possibilities, the number of processes multiplied by the number of interleavings. Okay, so now let's go back to the problem, initial problem, which is the queue. If you have any question, please stop me. So we want to implement a queue, and the queue we want to implement it on 3 machines. Why I'm saying 3? Simply because we want to tolerate, let's say, 2 failures. So we put them on 3 machines. We could have much more. So in Amazon, I was taking the example of Amazon, every critical piece of software is running on at least 3 machines. Whenever you have something critical, you have 3 machines. Sometimes it's not enough, because if the 3 machines fail, well, they have to stop everything. But they have at least 3 machines. So what is the problem that we need to solve when implementing an object like a queue on 3 machines, for example? Well, let's think a little bit abstractly. We have a state of the queue, and the state of the queue is the elements that we put in the queue. I want to buy a book, this is an element to put in the queue. I want to buy music, this is another element, etc. And we have clients. This is me using Amazon. I invoke some requests, I call them rec, and I get back a response, okay, to simplify. And the response is, of course, a function of the requests. There are 2 properties that I'm going to read, and they're actually very easy, very simple, that we need to satisfy if I'm implementing my queue object on several machines. Let's start with the second one. Are you familiar with liveness and safety? Okay, whenever you define a problem in concurrent and distributed computing, the best way to define it is to divide the properties you want to ensure into 2 parts. One of them is called safety, one of them is called liveness. Safety says nothing bad should happen. Liveness says something good should happen. The combination of the 2 categories define your problem. Okay? In the case of a queue or an object, safety says the following. If I have a client C1 that is using the queue, delivering, we say delivering, that gets some response from the queue, and the response is a history. It's a history models the response. And there is a client C2 delivers a history, then one of them is prefix of the other. What is this saying is simply the following. Even if I have several machines implementing my queues, if 2 clients access these machines behave as if this client comes first and then this client comes second, or vice versa. There is no interleaving. Okay? This models the fact that the machines model a single queue. Okay? This is the notion of prefix. Either this client came first or this client came first, even if things are interleaved. Okay? So this is the problem we want to solve. But we could easily solve this problem by saying, okay, I want to implement an algorithm that whenever you want to access doesn't respond. This will be safe. An algorithm that does never anything is safe. Okay? If you don't say anything, you will never lie. That's safety. Okay? But I want my algorithm to be safe, but also live. Liveness says something good should happen. So what is the thing that should happen is the following. If a client C invokes a request, is using the queue, then C eventually delivers a response. There is a response. So this means the queue has to say something, has to say this is the next element, this is the next element, etc. Okay? So this one alone is trivial to guarantee. This one alone is trivial to guarantee. You just send everything. The combination is the difficult problem. Are we together? So the problem of implementing an abstraction of a queue, for example, on several machines, is this problem. Okay? If something is not clear, stop me. Okay, so now assume this is the problem we want to solve. Remember, you wanted to apply for a job at the new Amazon in Moscow. They hire you, they ask you to implement a queue, and they tell you what is the best algorithm. If you don't think carefully, you start thinking of a single machine. And you give an answer. That no, this is the internet. Turing is dead a century ago. There is no universal machine. You need an adversary. Okay, you define an adversary, you define your problem, and now the question comes back again. What is the best algorithm to solve this problem? As we just said, it depends on the adversary. If the adversary is very, very nice, I have a network of machines and the network is under control, there is no problem whatsoever. In fact, I'm not going to go into the details, but the complexity is 0 step. So what does it mean, 0 step? It means the machines on which I'm implementing my queue don't even need to communicate. If I assume that I have an adversary that is very nice, remember the adversary that I assumed is sequential. Sequential means every client comes after the other. They come very nicely. So if I come first and I ask the queue to store something, the queues do not need to communicate, okay? Because there is only me. I come, I get served, and then when I go back, they can communicate. So the complexity is 0. I'm taking an extreme case. There is nothing like a sequential adversary, really. There's always some interleaving. What if I have an adversary where there is concurrency? And in the real world, there is concurrency. When I go to Amazon to ask for something for Christmas, there are millions of people doing the same. So there is concurrency. So here we can show that the complexity depends on K. What is K? K is the number of people accessing the queue at the same time. We call it contention. Okay? You don't need to remember these details. What is important to remember is, which is not surprising, the complexity of the algorithm depends on the assumption we make on the network. We call this assumption adversary. What if I have an even worse adversary where my machines can fail? Some of my machines can fail. And this is a natural assumption because the reason why I have put my queue on several machines is because I'm assuming that some machines sometimes fail. And here the complexity will not only depend on the amount of contention, but the number of failures that can happen, n, etc. If I go even worse and I assume that my network can be completely asynchronous, what does it mean asynchronous? It means the machines communicate, but there is no bound, there is no upper bound on the time it takes for them to communicate. This is called asynchronous. Okay, they communicate, messages arrive, but I cannot assume that they will always arrive within 1 millisecond, or within 2, or within 3. Then, in this case, complexity is infinity. We can show that there is no algorithm, really. Okay, so what I want to stress here is, I have taken a simple example, a queue. And if you want to answer the question, what is the complexity of a queue implemented on a number of machines, depending on the adversary, you have several situations. Okay? So when we go from centralized to distributed, situation becomes difficult because of this guy. Okay? There is nothing like a universal machine. Unfortunately, even if the world of computing is so nice when we have a universal machine, here there is no universal machine. If it was universal, we would have one adversary and things would be equivalent all over the world, but it's not. And that's one of the reasons why it's complicated. This new parameter. Okay? Any question? Okay. Now, what happens when we go from algorithms to systems? Here I have been talking about algorithms, and the results that I have been talking about are theoretical results. People have been publishing papers showing that in this case it depends on contention, in that case it depends on the number of failures, etc. But now, assume you passed the first test and they hired you. They say, oh, this guy knows about distributed algorithms, know all these things, we hired the person. So they hire you and they ask you now, okay, build the system. You have this idea about this algorithm, but we want to show your system running. So we're going to hire you for 3 months or 6 months, and we want to see the queue running. Okay? What I'm going to claim here is that indeed there was a difficulty here going from centralized to distribute, but when you go from algorithms to system, there is another difficulty that I'm going to talk about. So let's go back to this queue. We want to implement a queue, the abstraction of a queue. Clients invoke this queue, and then this queue is implemented on several machines, which means there are several copies of the queue, and these queues communicate by messages. What do people do today? Do you think if you go to Amazon one day, I don't know, maybe you will visit them, or if you go to the next Amazon, which may be in Moscow, do you think people will build an algorithm here when they assume one adversary and they have an algorithm that solves the problem, which is implementing the queue, against that adversary? Do you think this is what they do? And the answer is no. And this is very confusing, because I just explained to you that it's important to assume you have an adversary, and you prove, you test your algorithm works against that adversary. Now I'm telling you that's not what people do, what engineers do. They don't do that. if you ask them, what is the complexity? You go to Amazon people, and it turns out that I know very well the director of research there who used to do distributed algorithms. You ask him, what is the complexity of your algorithm implementing the lock manager or the queue or whatever? And the answer will be something like this, and I'm going to explain. And if you think about it, it's not surprising. What they do is that they don't assume one adversary. They assume a vector. And the reason of the vector is the following. They say, in the worst case, the adversary is going to be this guy. So they're building the same system, but the system is supposed to be correct even if the adversary is this one. So if the adversary is this one, which means if there are a lot of partitions in the system, a lot of overloading, messages get lost, etc., the algorithm doesn't respond bad things. It might get slower, but it doesn't respond bad things. In the terminology I have used, the algorithm will remain safe. Okay? It might not be live, but it will remain safe. If the adversary is this one, the algorithm will respond with certain complexity. If the adversary is this one, the algorithm will respond with certain complexity, etc. So what they actually do, even if they don't write it this way, they don't care about mathematics, they don't write this, they just build systems, they don't care. But what they do is this. They assume a vector of adversaries, and their algorithm is actually an adaptive algorithm. Of course, they don't express it that way, but if you read the algorithm and you think about it a lot of time, you realize what the algorithm is doing is adaptive. If the algorithm is the worst, this is going to be the complexity. If the algorithm is this one, this is going to be the complexity, etc. And this makes it amazingly hard to understand, prove, test, anything. So the reason why it's so difficult is because these people who build these systems, they want to be able to tolerate bad situations, but if the situation is not that bad, they want to be fast. You see what I'm saying? So it's like saying, prepare for the war, but hope for peace. So this is what they do, right? So if there is peace, they don't want to pay a lot of communications. They want to pay less. But if the situation is bad, well, they are ready to exchange messages, etc. So this is why the algorithms are so complicated. It's because there is the notion of an adversary, and the adversary is not taken alone. It's taken as a vector. Okay? It's like a polymorphic adversary. Do you remember polymorphism from computing, programming? This is exactly what's happening. An example. Have you heard about an algorithm called Paxos? Maybe some of you heard about it. If you go today to, for example, a place like Google, heard about Google, in Palo Alto. So they use this algorithm. This algorithm, Paxos, is a famous algorithm because it solves this problem of duplicating state over several machines. The problem I mentioned. It's used, for example, by Google. It's, I don't know, thousands of lines of very complicated C code. In each implementation, why in each implementation? They have tons, they have maybe 12 implementations of this algorithm. In each case, it's the same problem. What is the problem? They have a vector of adversaries, and if the situation is this, they do that. If the situation is that, they do this, etc. It's extremely complicated. They have a huge number of engineers just taking care of this algorithm, the same algorithm. But the algorithm is a nightmare. And it's an example of why this area is very difficult. Okay, Act 1, from centralized to distributed, you need one parameter. This is what theoreticians do. When engineers do, is they don't add one adversary, they add a vector. Okay? So when you go to systems, you add all these guys. So now, oops. What is adversary-oriented computing? Okay, so now I highlighted the fact that writing distributed systems is difficult. And I would like to suggest a way out. And of course, this is just an idea. We started working on it for a couple of years. It seems to be promising. The idea of adversary-oriented computing is, in a sense, trying to reduce this problem of handling several adversaries at the same time into the problem of handling one adversary at a time. I would like to explain how this works. Let me go to the main point. The best analogy to this idea is the following. Who has ever programmed with a switch? Remember the switch? For those of you who are too young, anybody doesn't know what a switch is? If you are under 10, you don't know what a switch is. Okay, you all know what a switch is. So a switch is a fantastic programming construct. Why is it fantastic? Because it enables you to say, I have an algorithm, and my algorithm is going to adapt. Okay, this is what the switch. It's adapt to what? It's going to adapt to different conditions. Okay, when you write with a switch, you say, for example, this is Yandex employee, switch age, if age is under 10, do this, if under 20, do this, if under 30, do this, etc. So you can write all the situation conditions here. The idea of adversary-oriented computing is similar. Of course, it's just an idea of the mind. Is to say, I want to write an algorithm the following way. This is what I would like to write my algorithm. Switch my adversary. Okay, the parameter is not the age of the employee, it's the adversary. If the adversary is A1, do this. If the adversary is A2, do this, etc. So what is nice here? The nice thing here is that I can focus on each algorithm separately. Prove it correct, test it, debug it, and then plug it in my switch. If this algorithm, if the adversary is this one, then I need only to make sure that the algorithm, this one, is correct. Okay? If the adversary is this one, etc. So the way I do it is the following. I start with the worst case. The worst case is the strongest adversary. Let's that be AN. I do my algorithm. Here, I don't care about optimizations. I just need to guarantee that if my adversary is this one, my problem is solved. There is a little glitch here. The glitch is, but what if the adversary is not this one? Okay, this is the worst one. If the adversary is not this one, maybe is a weaker adversary, like this one. So for example, I'm assuming my network is going to be attacked. Some malicious attackers will be there. If I detect malicious attackers, this algorithm is going to execute. But if I don't see any malicious attackers, okay, now the situation is a little bit tricky. I execute, for example, this algorithm. So this algorithm is supposed to work well if the adversary, for example, is not malicious. Okay, there might be failure, but failure is simply a crash. There is nothing worse than that. So in that case, the mission of the algorithm is to work well under this adversary. But there is another mission that is hidden under this algorithm, which is the following. In case the adversary is bigger than this one, remember that adversary is a set. In case the adversary is bigger than this, which means there is an interleaving that I didn't plan for, this algorithm should abort. Should say, I cannot, this is not my job. I cannot do that. I cannot handle this guy. Okay? It's like in boxing, you send somebody to box another one, but the guy is twice bigger. Say, no, this is not my category. Abort. And then they call the other guy. Okay? So the trick when you write these algorithms is not only to solve your problem against an adversary, but you solve a slightly more difficult problem. The more difficult problem is, if the adversary is not this one, you have to abort. But you have to abort by saying, I cannot continue. Here is my current state. Okay, I won't go into the details, but there is a little difficulty here, which is, I thought the adversary was this one, but it's not this one. Here is my state. And then the algorithm continues with the other adversary. What I want you to remember from this idea of adversary-oriented computing is simply this picture. Of course, you will ask yourself, but how can this work? Well, this is exactly what I want you to ask yourself. How can this work? So there are some cases where we have shown that this works very, very well. Remember the Paxos example, the big algorithm that is driving crazy a lot of people. We could actually significantly simplify it by extracting 5 different adversaries and 5 different algorithms, sub-algorithm, each one solving one particular case. So there are situations like that where you can do it, and you can show that it saves you a lot, because you simply test this, and then later on you test this, and you test this. If you find a better algorithm for this guy, you remove this one, and you put the other algorithm. So I don't want to go into the details because of time. So there are, if you are interested and if you are writing distributed algorithms and you want to see how this idea works, how this switch idea works in practice, there are a bunch of papers. So in academia, what we usually do is when we have an idea, we write papers. Some papers are purely theoretical, you prove that things work, and some papers are actually practical. So you show that certain experiments work well and the results are pretty interesting, etc. So for those of you who are interested, I will be very happy to give some examples of concrete switches where you can actually build your distributed system in a modular manner. So these are some cases. So for example, in this case, we show that in a situation where you can have malicious attacks, you can compose protocols. This paper is about multicore algorithms. So it's about scheduling and the way you can build algorithms like that. So this is what I told you before about these Paxos algorithms, where we could show that you can actually simplify significantly by at least 1 order of magnitude the proof, the test, and the optimization part by writing it as a switch. Okay, I don't want to be longer than expected. I simply wanted to give you an idea of this new approach to writing distributed systems. I didn't say much, I know, but in 1 hour it's hard. What I wanted to do is highlight the main problem. The main problem is people typically have to deal with vectors. The idea here is to reduce that problem into a simpler one, where in each time you care about one adversary. The way these things work, I didn't talk about. But if you are interested, I'm here for the rest of the week and will be happy to talk about this. Okay, the way you could view this is simply the following. Have you heard about, remember object-oriented programming? Yes, good. So in object-oriented programming, they told you, you have to divide your program by looking into the data. And the data you have to be, it has to be your modularity dimension. Well, adversary-oriented computing says something complementary. It says the control of your algorithm, if you are writing a distributed system, should be another dimension of modularity. And this control depends on the adversary. Thank you for your attention. It's exactly 1 hour. Thanks.
Excuse me, do you publish your simplification of Paxos algorithm?
Yes. Yes.
Is it mentioned in this list of publications?
Yes. The 700, there is a paper called the 700 BFT protocols.
Oh, okay, thank you.
Paxos is a family. So in this BFT protocols, there is a family of Paxos algorithms which tolerate malicious behavior, etc.
Mm-hmm.
Yes.
I've got a question. I think that kind of differentiating between different kinds of adversaries might be quite computationally complex. Like you can differentiate between delays and partitions because kind of it might look the same.
Yes, this is a good question. In fact, so the question is, what happens if the adversaries look the same? What do you do? Okay, so for example, there is a delay, you don't distinguish between delay and partition. So it is important here to say that this idea of programming things that way is not going to solve that problem. This idea simply says, if there is a way to solve that problem, okay, so if there is a way, if there is an algorithm that adapts to different adversaries, assuming there is one. My claim is, if there is one, my claim is, you can write it as a switch. But if there is none, I cannot invent one. You see what I'm saying? If there is an algorithm that can distinguish, but you're right, you cannot distinguish between sometimes delay and partition. In this case, the switch doesn't help you. But if you can distinguish, if there is an algorithm like Paxos or like others, I claim that you can always write it as a switch. I didn't prove it. I still have 5 years. But I claim that you can do it, assuming this distinction is made.
So actually you're taking adversary detection as a black box and you use it like an external module to detect what kind of adversary you're facing right now. Right?
It's a good point. In the examples we have been considering here, the answer is yes. But sometimes it cannot be a black box. For example, if you want to detect something that's of particular interest, you have to put it inside your algorithm. Yes. Yeah.
And another question. So usually when distributed system faces a failure, you have to somehow recover from it. And therefore, if you started to progress on executing one algorithm, you should devote some attention to roll it back and to recover a valid state to run another round or recovery protocol or something like this. So how do you handle rollbacks between two algorithms?
Yeah, that's a good question. So it's everything is hidden here. Let me just go back because to illustrate, if I'm fast enough. So it's all in the switch. Magic switch. Okay, so the question is the following. Assume, for example, the switch starts and then you assume you have an adversary where the system is completely sequential, there is no contention. Let's say it's night and there are very few people using your system, there is no sequentiality nor nothing. You start by executing a very fast algorithm. The fast algorithm goes to the queue, put whatever in the queue and terminates. But then just before terminating, the other machine says, be careful, be careful, be careful. I have seen another request coming from somebody else. Therefore, there is contention. Okay, which means this adversary is not as easy as we thought. We thought it would be sequential, but it's not sequential. So we have to go here. Go here is like recovery, in the sense that what we are saying is what we started doing here doesn't seem to be correct. We have to abort. We have to abort and go here. This part, which I didn't explain, as I said, because of time issues, is not trivial. However, we can precisely define the problem that you solve. The problem that you solve is the following. If the adversary is this one, execute this algorithm correctly. If the adversary is not this one, you have to safely abort. Safely abort means I switch to another adversary with a safe state. A safe state is a state for recovery. And I didn't say anything about it, but it takes time to explain. But you can define precisely what is this recovery state. We can talk about it if you want, but in 5 minutes it's hard. I'm simply saying the problem solved by this algorithm is not simply if this adversary is A1, be correct. It's also, if it's not A1, you give a safe state. I didn't say what a safe state is. I'm simply saying that this is the problem.
Excuse me, who makes a decision of the adversary level? Because you have to compute it twice. First time in switch, before switch, and the second time in each algorithm when it decides can I handle it or I cannot handle it.
Yes. So the designer of the system, so assume I'm designing my system. I know that the worst case is this one. If I have worse than this, I cannot do it. But there are other cases where I can have optimization. So I'm the designer, right? So I write the switch. But when I write the switch, I have to write these algorithms. Okay? Again, I'm repeating myself. The task of this algorithm is to do the following. If the adversary is this one, they have to terminate. But if the adversary is not this one, they have to detect it. Because if they cannot terminate, they should be able to abort. So this algorithm, the task of this algorithm is to check if the adversary is not this one. So to answer your question, there are two levels of the level of the designer of the whole system and the level of the implementer of this algorithm. The implementer of this algorithm should say, oh, there is contention. I cannot do it. Here is my state. And this state should be safe. I didn't say how it is because it took time, but this is.
You mean just you check if input parameters are not in the
Yes,
right range,
yes.
so it's not mine.
Yes, but it's not always easy because sometimes the input parameter there is, for example, messages get lost. So this is the input parameter. So it's not as easy as the age, as checking the age. Yeah.
So let's consider, let's say, blind designing, and if you do a design of your architecture with not well-defined cases, probably I don't know, the state of your system cannot fit any of your case. That can happen, and how can you solve this complexity?
So to understand, you say assume the adversary can be anyone. Yeah, well, in that case, is like saying, again, think of the analogy. It's like saying, I have a nice algorithm that, depending on the age of the employee, does different things. If I understand you correctly, you're saying, what if you don't know the age of the employee, right? Is that the question?
Probably yes.
Yeah, if you don't know, then this is not going to help you at all, because this is designed for situations where you can distinguish between adversaries. Because the current situation today in distributed systems is, even if you can distinguish, the algorithm and the system is still a nightmare. Even if you can. What you're saying is, what is the if you cannot? Well, if you cannot, it's even worse than a nightmare.
But for example, if you, I don't know, write a couple of algorithms and some part of the system changes, you should change the part of algorithm.
If you already write your algorithm and you want to change later.
Yes, probably that bring, I mean, this casing of a lot of algorithms probably bring more complexities than solve it.
Okay, there is something interesting here. Remember what I told you, the adversaries are sets. A good design strategy is that this is the biggest set. This is the worst case. Okay, this is typically the situation where you say, if none of these adversaries is okay, I will go with this one. As long as you are in this one, you have the worst adversary, there is something interesting here. Your system is running, assuming the worst case. It's actually feasible, while the system is running, to add on the fly another case for a weaker adversary. It's easy to do because you are already in the worst case, your algorithm is running. This is going to be slow. But nothing prevents you from saying, I have an idea, if there are only 2 failures, for example, I have an adversary AK prime, and I can do another algorithm. You can plug that algorithm on the fly. Of course, you need to make sure that in this situation, from time to time, you go out and you check if the adversary is weaker.
And the last question. So what are the examples of practically detectable adversaries in near real time?
So in the cases where we have looked at, the cases are typically timeout. So for example, a message has taken more than expected. This is a timeout, so this is easy to detect.
But adversary should span the entire system, right? So a timeout is a single event happening in a particular link.
Yes.
But what happens? Shall I reason in terms of timeouts happening in the entire network, or shall I reason of failures happening in my neighborhood?
Right. Now, I'm going to give you a concrete example. Assume here I'm saying if my system is synchronous, my algorithm is very efficient. Synchronous means between every pair of machines, communication takes at most, let's say, 1 millisecond. Okay? Every pair of machine, 1 millisecond. If that happens, I'm going to use this algorithm, and this algorithm is very fast. This algorithm should solve the problem if the system is as expected, but the algorithm should also detect timeouts, meaning if I'm a machine, I'm waiting for a message from Ivan, and after 1 millisecond, I don't get a message from you, this means I abort. For me, it's over. And I should have that, of course, all over in all machines. Whenever any of them detects a timeout, it says, oh, oops, This is not the adversary that I'm able to handle. I should abort. So it's kind of a distributed adversary detection. You can have the same idea for contention, you can have the same idea of malicious attacks or whatever.
So we can run different algorithms on different machines in our system. That should be okay.
As long as for every adversary is something distributed, right? It's for intent. As long as for your adversary, the algorithm, the distributed algorithm that you're running complies with the contract. The contract is, if this is the adversary, I solve the problem. If it's not, I abort safely. It looks like magic, I know, because I spent most of the time highlighting the problem. But that was my goal, because if I needed to go into these details, I need another hour. Maybe next time.
So, last question.
Would I be correct to say that the goal of your research is ultimately to outline the best practices for software developers to reliably build concurrent and distributed software with this kind of switch approach implemented in the process of development, like the best practices for programmers?
Yes, thank you for the question, because the answer is easy. Yes. Yes.
Figures.
Okay.